我叫陈佑良，因为平常比较习惯性用英文来 present， 所以我整个 presentation 就会用英文，所以请耐心听。Okay, hi everyone, I'm Youliang Tan. So today the title of my talk is about building generalist model for robotics, and specifically on humanoids and manipulator. So I'm from NVIDIA Research, specifically the gear team. My daily routine is about building foundation model for robotics. So let's get started. We have generalist agent, right? I don't need to convince everyone that generalist is better than specialist, as we can see from a lot of the models, out there like ChatGPT, Cloud, or Gemini. And also, on the other spectrum, we can think game agents as new embodiment, similar to robotics. We have also seen better results, some research initiative like Gato and CMAR that works on a generalist model for game agent. But where is our generalist model for robotics? So before going into the definition of a robot generalist that everyone talks about just now, let's think back as we humans. So we humans are kind of a generalist from one spectrum. Our brain is kind of like a generalist. We can quickly adapt to various kind of like action spaces or new embodiments, right? Imagine you have various games on your game console. You can control immediately using a game console or keyboards to control the game avatar, despite whether is it continuous space or discrete space. Similar to we doing behavior cloning on different kind of robots. We have different kind of teleoperation device like VR headsets or Aloha setup like Puppeteer approach. Teleoperators are able to immediately kind of, maybe with some practice, they are able to use the teleoperation device easily and control robots. Same as driving a car. We can transfer the knowledge from driving a sedan to an SUV. So we humans are generalists, so we are able to master the well with some RL practice or some imitation learning by watching a video from YouTube. So similarly, we can assume that a robot generalist is able to perform different kind of tasks or on their embodiment of avatar with certain context, as long as it's within affordance. So to achieve that kind of generalist capability, we need to think of like different spectrum of scaling. This is more like the capability spectrum of how we want to scale this generalist capability. Normally, when doing behavioral cloning, we will think about like first, work on a single task well, simple motion, then dexterous motion like folding clothes, and also long horizon tasks that might require reasoning. Then it goes to multitask scenario, if we are able to do single task well. And research has shown that when we do multitask, we train multitask data set, it actually performs much better than single task, the research from TRI. So with multitask conditioning, we can able to boost up the performance for in-distribution tasks, definitely. And we can use different kind of tricks, like leverage on priors from other places to make it perform better for our distribution tasks. And a generalist shouldn't only work well on one single embodiment, right? And even for a robot company, they might have different iterations for building different kind of robots. So we want to enable certain multi-cross embodiment support. So this makes the entire problem very hard. How you define different kind of embodiments? Is it when you change the sensor configuration, if you add an additional degree of freedom, do you consider those as a different embodiment? I would think so too, because the kinematic chain is essentially very different. And also, when you switch from a humanoid to mobile manipulator, it's also very different. The OpenX cross-embodiment project, which was launched 1.5 years ago, kind of shows certain improvement when we train it with cross-embodiment data. But that's with the assumption of unifying the action space and effective action space. So we need to do more study on this cross-embodiment data, which I think kind of provide certain insights. It does help, but we need to do more rigorous study on that. And about this robotics Merivac's paradox. We always hear about Merivac's paradox, right? Reasoning is easier than sensory and motor skills, perception skills that we see in advancement on ChatGPT or whatsoever. So Yesterday, Jim from my group kind of talked about this. I kind of have an extension thought of this. So we always see a lot of like cool dancing robot dance, or maybe that humanoid can also dance, I don't know. And they are normally trained with simulation with RL and able to transfer real in the world. Unfortunately, on the other hand, like imitation model kind of failed often in OOD scenario, our audition scenario, which kind of makes sense from human intuition that it should be able to recover from that behavior. Like the SO101 robot that I trained, sometimes it got caught in the cup. I only trained it with 30 trajectories, and then it caught in the cup, and if we are able to use reasoning well, it's able to lift up from that OOD scenario and then start to grasp another object. And also from a Bomba Aloha failed setup, the spatula actually got stuck. And this kind of scenario, OOD scenario, it happens regularly. New scenes, new tasks, new skill sets. And the way of countering this right now is to gather more data. But I think that we still have the gap of imitation of motion is easier than bridging the gap between motion and reasoning space or understanding space. So this is another paradox within the robot learning domain itself. That's why we have like the trendy thing about vision language action model in the wild. There's NVIDIA GROOT and 1.x, Gemini Robotics, and physical intelligence. They kind of have the same recipe, right? Having a VLM, having another DIT or flow matching architecture that kind of bridge that gap of world understanding and also the motion imitator side of low-level policy. However, we still get certain gap of generalization that we really hope to achieve. Zero-shot capability, etc., etc. So here, we kind of want to, we can see the transformation of AI from specialist to generalist and specialized generalist. And on the spectrum, I would also argue that we want to see that kind of trend, going from generalist and specialized generalist. So Stephen actually talks about ASI. Yeah, I assume it's more like a specialized generalist model. So you can either do it from the generalist side to transform to a specialist side with post-training, or you can straight away go for ASI and then do get all this rollout to train a generalist. I think both strategy actually makes sense. From the model, just now, those are from a model perspective. And we can also see the cost of robots actually going downwards, right? Just 2 days ago, we see Unitree just released like a 6K R1 robot. And it's very attractive that robots cost actually goes down tremendously, which helps in the advancement of robotics and body AI. And why we use humanoids or mobile manipulators. So I would like to take note of the conversation we have is not about automation, but it's about autonomy. So we want to create this kind of generalist solution that is able to, robot autonomy that is able to perform in open world setting. It's able to zero-shot to integrate to human world infrastructure without making any modification to the environment, which is not the case for industrial automation. And data, there's also a lot of internet data that we want to leverage on. And by manipulators or humanoid, they kind of make sense. So why we focus on humanoid? Because I think humanoid is a more researchy area that have a lot of advancement. But by manual manipulation, the parallel drawer gripper definitely is an easier way of doing things. So here is also another difference that we can see from robot foundation model and state-of-the-art AI foundation model. The data essentially, the difference in data is essentially quite huge, that it's hard to bridge the gap. So we want to also find a way to leverage on this prior from the web data to train our foundation model. So moving forward, moving towards our GROOT and 1.5 vision language action model. So this was one of the projects that I work on in our research group. So we kind of train our vision language model to try to tackle the problem of generalization. Although that's not the final recipe, but it's a path towards trying to solve the generalist problem. So 3 core principles here: a generalist, it has like a VLM or flow meshing architecture. Maybe it will change in the future. And also data pyramid that Su-Hang and also Steven actually talks about. So this is a robot foundation model. It's open source, openly available. Everyone can kind of use it to post-train it with their data and with their own configuration for cross-embodiment. So what's new in M1.5 versus N1? So we released N1, I think last March, and released an updated version 2 months ago. So there are a couple of improvements, like a frozen VLM that retains generalization, language understanding. There's also another paper from about GR3 using co-training approach to retain that capability of using co-training with vision language data and also robot data. I think that also makes sense. And we also enhance the VLM, swapping it with a different model, flat integration, and DreamGen integration that I can talk about later. The blog post is there. So to recap about vision language action model, right? Maybe some people aren't that clear. So it takes in image, robot state, and language prompt as input and output robot action trajectories. Normally it comes in a chunk. And most of the time when we are talking about this VLA, it's this part, the imitation learning approach. We have behavior cloning and reinforcement learning. So this imitation learning requires enormous amount of data. Human expert data, not necessarily human expert data, but it can be any expert data or robot data. And this is the model itself. I will skip, and the model architecture itself. So the data essentially is real-world data, and this is an example of a teleoperation scene. Okay. And we all know that robot data collection is extremely difficult and time-consuming. So this is two of our robots in our lab, and it's just doing one single task, and we need a lot of human effort just to collect this kind of data, and it's definitely very expensive. And how can we create another kind of recipe to augment this kind of data? So that comes with the data pyramid of real-world data, synthetic data, and web data. But I would still argue that real-world data is still very, very important. All this synthetic data or web video data, they are just surrogate data or augmentation to make sure that, to kind of complement the real-world data itself. This is a pre-trained data statistic that we use when we train GROUP M1.5. So we have in-house humanoid data, GR1, that we collected. And we also leverage on other cross-embodiment data like OpenX embodiment, Droid, and also AGI bot beta and alpha. And thank you so much. And we use it as our pre-training mixture during our training. And for the other front of synthetic data, we have RobotCasa that supports different kind of embodiment, and we do training with another recipe called Dex Mimic Gen. So Dex Mimic Gen essentially is a way of doing augmentation on the spatial augmentation to generate more diverse data. And then we also have a research. We also did this kind of analysis as sim and real co-training actually helps, like what Hang Sung actually talks about just